Okay, so today we are going to finish up analysis of variance. We're going to talk about mixed designs. And then next week we're going to hit correlation, regression, and then close with non-parametric stats. And the way I've sort of built the schedule in, there's a review session on our last Thursday before finals. If we get through it all, great, we'll have the review session. If we don't get through it all and we have to use that session to finish content, then we'll probably have a review session on the weekend or something like that. It'll be optional. You can come if you want.
Friday?
We might do Friday. That lab, I wasn't planning on having anything. So I'd rather do one review session rather than four. So we just have to see, okay? So, but hopefully we'll get through it all. But we do have a lot to cover still. Okay, so mixed ANOVA. Okay, so we're going to start this lecture out by just reviewing, going back over all of the analyses we've learned for the semester so far. And I'm looking for something in particular out of you. I'm not going to tell you what it is. I'm looking for something in particular out of you. And then when we get toward the end of this review, you remind me to tell you what that is that I'm looking for, okay? So we're going to gain some perspective here. Let's start by looking at different analyses. Okay, let's try the first one. You have a sample. You can compare it to a population where the variance is known. What kind of test?
Z.
Why it's a Z? Because?
Population variance is known.
Very good. Z test for sampling. How about, you know what? 1 second, give me 1 second. We'll pause for just a second because this did not. Okay, well that's all right. I have a streamlined version of these slides that I fixed, but I apparently didn't upload it, so it's still got the builder version. It's just the animations are a little out of whack, but it's okay. Okay, how about a case where the population variance is not known? You have a sample compared to a population. You don't know the population variance.
Sample t-test.
T-test. Good. Okay, sample with a treatment group, sample with a control group. They can only be subjects assigned to one of the two conditions. What is it?
Two-way t-test.
Two-way?
Two samples.
Two samples. Not two-way. Independent samples. Yeah. Reason it's not two-way, when we say way, that means the number of factors, right? So you can't have a two-way t-test. Okay. So independent samples t-test. Subjects at time 1, subjects at time 2. Same subjects. Yeah. Dependent samples t-test, also known as repeated measures. Right? Sample ordered in terms of scores on a variable like IQ. Sample matched based on scores on the same variable, so you're trying to control for IQ. Dependent samples t-test, also known as matched samples. Okay. Sample selected because of a personal characteristic, for example, a daughter, and then you select the mother because it's the mother of the daughter. Dependent t-test. Okay, good. Yeah, match samples. Sample. 3 conditions. Conditions are independent of one another, so folks are assigned to one group out of the 3, but not multiple groups. One way between group ANOVA. All make sense? Okay, how about this? You have factor A, you have factor B. Okay? And subjects are assigned to conditions, so you get sample means for each of those 4 cells.
Two-way between sample t-test.
Yep.
Or between groups.
Yeah, it means the same thing. Two-way. Okay? Where do we find the main effects? in the margins. So we could look at the mean for factor A condition 1 compared to the mean for factor A for condition 2. That gives us the, what do we call that? The main effect for factor A, right? And for factor B, whoops, we're going to look in those margins. Main effect for factor B. Good? What's that? What if we got a mean in one of the cells that looked really different from all the other means? It's an interaction effect, right? So it's an interaction effect. It could show up there. That's the A by B interaction. It could show up there. Still an A by B interaction. It could show up there. What would we call it? Right? And it could show up there. Still an A by B interaction. In other words, when you have a 2 by 2 design, you don't have 4 interaction effects. You have 1, but it could show up in any of the 4 cells. Does that make sense? Got to really know that for the final. Okay, so I want to make sure that you guys get that, because the quiz, that came out, that still wasn't clear. Okay? So, the interaction effects are by factor. Right? If you have 2 factors, you can only have 1 interaction effect. Where it shows up depends on your data. Okay? Okay. What if you were looking within factor A, just across the top row of those conditions? What kind of effect is that? In other words, you just ignore one of the conditions for factor A. Just look for differences within one of the conditions. What would you call that? This is a tougher one. We talked about it in class. We actually haven't ran these analyses, but we did talk about it in class.
Is this
Is
where
it?
Tukey's test would reveal something about that?
Not so much Tukey's test.
What'd you say?
It might be within if it was a repeated measurement. Okay, but when we look at slice and dice the data this way, that's a simple effect. Okay. Simple effect. You could go that way. You could also go that way. Okay. So if you look back over your notes on ANOVA, we talked about this a little bit, but I actually didn't have to run analysis on it, so that's probably why you don't recall. Okay. Okay. How about this?
Repeated measures within.
Is that again?
Repeated measures within.
Yeah, it's repeated measures. Well, the moment you say repeated measures, within is assumed. There's one other part to it. You'd say, how many ways? Yeah, so one way repeated measure, right? One way within group repeated measure, ANOVA. Can there be an interaction effect? Why not?
It's only one factor.
It's only one factor, right? So you're going to see changes in scores over time, but there can't be an interaction effect. You can only have an interaction when there are 2 factors more. Okay? How are you guys doing? Okay. So what do you think I was looking for out of you guys when we did this? Looking for a certain reaction out of you. A certain kind of reaction. I was looking, you want to know? I was looking to see if you're getting bored. Why?
You're exciting, aren't you?
Yeah, why would I look to see if you're getting bored?
It's only, you can only ever test 2 things, really.
You what?
You only ever test 2 factors.
Well, you can test more than 2. I'll show you in a little bit, testing more than 2 factors. But in terms of like going over these tests, I was looking to see if you were getting bored, and the reason was, if you're sitting there and you're kind of thinking like, this is so old school. I mean, we've done all this. We don't really need to go over this again, right? That's a really good sign, right? We want to get you to the point where you can look at these designs and just say, oh yeah, that's a t-test, or yeah, that's an ANOVA. Okay, I know when we need to run that, what we can look for, what we don't have to look for. That's a good sign. If you're feeling like, hey, that all looks familiar to you, right? Think about if we were back at the beginning of the semester. If I had just done that at the beginning of the semester, would you have had the same reaction? Probably not, right? Okay, so yeah, so good news. Okay, so what is a mixed ANOVA? There's at least two factors, okay, and at least one between subjects factor, and at least one within subjects factor. Usually there's only one within subjects factor, okay? But you could have multiple between, okay? The slides that I'll upload later actually get you through this little transition better, but that's okay. So the key features to a mixed design, sometimes it's called a mixed between within design. If you just say mixed, you don't know what you're talking about. But you have to have at least one between subjects factor, one within subjects factor. So, examples. 2x2 mixed ANOVA. In this example, we would have a between subjects factor of sex with conditions of males or females. Okay? And a within subjects factor of time, in which the time factor is divided into two levels, midterm final. Okay? And the dependent variable would be exam scores. Okay? So, question came up in the morning class. Well, why do you call the within subjects factor time when it's the midterm and the final? Those sound like very different things, right? Why would we still call it time?
Because the class has progressed, time has progressed between these two things.
Right. So with the exam scores, you're getting exam scores on a midterm, an exam score on a final, and there's an interval of time that has passed between the two. So you're still looking within subjects. You're looking at the same person and their score on the midterm versus the final, right? The key part to within subjects is that there's an interval of time that has passed. Okay?
Is it always time?
It's not always time, because you could have, for example, all the measurements done simultaneously, but what you're looking at is the same person's ratings, say, of the taste of a particular cake, right, which was an example that we used before. Okay? So it doesn't have to be time. You can still do within subjects where the time is, the ratings are still done sort of simultaneously, very, very close in time. But usually it's time. Okay. But within subjects, it doesn't have to only be time. Yeah, the slides that I have do these animations a whole lot better. Okay, so we end up with a 2x2 mixed ANOVA that looks something like this. You'll have a score for time 1 in group 1, time 2 in group 1, okay? Time 1, group 2, time 2, group 2. Okay, so you have a main effect for the condition of the group, a main effect for time, and then a time by group interaction. How are you guys doing? Pretty good on that? Sort of? Have to look at it a few times. Okay? So, let's say we did a pre-test, post-test with males and females. It would look something like this. Right? Pre-test males, pre-test females. Post-test males, post-test females. Those would be our 4 cells. How many interaction effects? 1. Where would the interaction effects show up? Yeah, in any of the 4 cells. Okay? But only 1 interaction effect. Okay. So that looks like what? Yeah. One way within group repeated measures, right? Okay, but the moment I add this, it becomes 2x3 mixed. Does that make sense why? Yeah? Okay. Where are my main effects going to be? In the margins. So if I want to look at the main effect for time, I'm comparing the means for level 1, 2, and 3. That's a main effect for factor B or time. Okay. If I'm looking for the between group main effect, those are comparing the means for factor A across conditions 1 and 2. That's the main effect for factor A, between group factor. Okay. And then the interaction effect can show up anywhere in those cells. I just happen to highlight top right quadrant. But it could go anywhere. You could also have interesting combinations. That would be an interaction effect, right? How about this one? Yeah, it depends on how the means shake out, right? You might see a main effect and an interaction effect and something like that. Okay? Point is, you get one interaction effect, okay? But there's lots of different ways it can show up in the cells, in those means. That make sense? Okay. What if I just want to look at that bottom row? What would it be? Yep, simple effect. Okay. You guys were good at that. I went through that pretty quickly. Must be the end of the semester. You guys are just all over it. You sort of like those synapses are firing. You've got all semester to practice. Neurons are going. Okay. Time to play with the Rubik's Cube. Okay. Now, you will see in your literature reviews studies that employ designs, and they'll note them as like 2 by 2 by 2, 2 by 3 by 3, 2 by 3 by 2. And you might be like, oh my goodness, what does that mean? Okay. And what kind of effects should I expect to see in the results section? Okay, so good question. In order to sort of address this properly, we have to take a little bit of a conceptual leap and start thinking about our effects three-dimensionally. Okay? So up to this point, when you had two factors, we could think of them just in terms of 2 dimensions. Right? Now we're going to have to add a third dimension. Okay? And the good news is a couple of things. One is, I'm not going to actually have you do these analyses in lab, but I do want you to understand what's going on. Okay, so you're not actually going to run a 2 by 2 by 2. It's not all that hard to do, but it just starts getting complicated. I haven't even gotten you to 2 by 2 mixed yet, so we need to do that first. Okay. The other bit of news is if you go to grad school, okay, you're going to run into these things, and they start getting more and more complex because the more variables that you start taking into account in your research, the more dimensions you have to consider. In fact, if you take a course in factor analysis, what you'd be discussing would be the relationship of scores on any one item or scale to multiple dimensions, sometimes 10 dimensions. Okay? And so every score would have a relationship to every dimension, which means you now have to think about hyperplanes and a conceptualization of space that goes beyond 3 dimensions. Sound like fun?
Sounds cool. So much fun.
So when I was in grad school, my stats professor was talking about, he was talking about these planes of dimensions that would all intersect each other at different angles, and any given data point would be in relationship to every single plane, and that's how to interpret the data. I was like, I have no idea what you just said. Right? So you don't have to worry about that for this class. But we do need to think about, at least conceptually, what does the 3-dimensional model kind of look like? So if we had 3 factors, we might say, okay, For a mixed design, we'll have 2 between group factors and 1 within group factor. So our between group factors could be sex and treatment. Okay? So the conditions within the between group factors would be males and females for sex, and then a therapy treatment group or a control group for treatment. Does that make sense? The within subjects factor then becomes pre-treatment score and post-treatment score. So let's imagine we're doing a study looking at cognitive behavior therapy for individuals, and we're going to measure them prior to treatment and at the end of treatment. Does that make sense? Because our individuals are not just males, we have males and females. Good? Okay. So here's our within, and these are our between factors. So how many main effects do we have? We have a main effect for each factor. So we're going to have a main effect for sex, a main effect for treatment, and a main effect for time. Okay? So let's take a look at the main effect for sex. What are we saying? Well, the main effects for sex is the effect of sex on scores irrespective of treatment or time. Okay? So main effect for sex irrespective of treatment or time. So this would be equivalent to saying, for example, and the reason I highlighted the yellow cubes, right? Imagine in each of these cubes there are means, right? So the mean for this cube is the mean for males in the control group at pre-treatment. Does that make sense? So this cube is pre-treatment scores for males in the control group. This one would be pre-treatment scores for males in the therapy group. Does that make sense? This one would be post-treatment scores for males in the control group. And this one would be, what kind of scores?
Post-treatment.
Post-treatment. Say it again.
Males in the therapy.
In the therapy group, right? Okay. Now let's say that in this example, lower scores are better. Like you get lower depression scores. That's a good thing. Okay? So what you'd be saying is, look, across all males, irrespective of their treatment, right, or the time they were measured, pre-treatment, post-treatment, they had lower scores than females. Right? Is that good news or bad news for us from a research perspective?
Bad,
Why bad?
because we want all genders to respond the same to therapy. Hopefully, we don't want a therapy that's only effective for guys.
Yeah, and the thing is, it's not even in response to therapy. They were different, apparently,
Yeah.
maybe at pre-treatment,
Yeah.
right? So the men would just have lower scores.
That's kind of true, though. Women tend to experience depression at a higher rate, so.
At a higher rate, yeah, whether their scores of the folks who come in are higher, yeah.
Okay.
But yeah, do you see what that means then? It means irrespective of time or treatment, the males had lower scores. That doesn't really speak directly to a treatment effect, right? It just tells us that men are different than women. So that doesn't really have a lot to do with treatment. Okay? Okay, let's take a look at the next one. Main effect for treatment. So if I highlight these cubes down here and say that those gold cubes have the lower means, okay, now what am I saying? I'm saying there's a main effect for treatment, meaning what?
Treatment lowered scores.
Well, the way to think about it is that the treatment is conditioned. You're either in the treatment group or the control group.
If you go through therapy, you have lower depression scores, irrespective of sex and time.
Yeah, so the first part is where I'd stop you and say, if you go through therapy, because look, these folks right here, hadn't gone through therapy yet. In other words, what we're saying is that the treatment group has lower means than the control group, irrespective of phase of treatment, whether it's pre or post, in terms of time. Does that make sense? So this might be good news. It might not be good news. It might tell us that maybe the groups were different to begin with. Maybe we had some sort of issue in that we had folks who were in the treatment group who just weren't as depressed to begin with, right? That would account for a main effect for treatment, right? Is if those folks weren't as depressed to begin with, then surprise, surprise, they had lower scores at treatment and lower scores post-treatment, pre and post. Does that make sense? Okay. And then we have one other thing we can look at, which is a main effect for time. And in this example, the gold is highlighted on the post-treatment scores, so the post-treatment means were lower. Okay. What does that suggest to us? Is this good news or bad news? Good news?
Yes, because post-treatment is higher.
Lower scores.
I mean, post-treatment is lower scores irrespective of sex. And, oh, wait.
Ah, there you go. I was waiting for that to come in and hit you. What happened? So what is this suggesting to us? There's lower scores post-treatment, but it's lower scores for both the treatment and the control group.
Yeah.
Right? This is what you would get if you had a placebo effect or regression to the mean. Okay? Meaning that, sure, scores in the depression scores in the treatment group went down, sounds great, but they also went down in the control group where nothing happened. So that drop in scores may have nothing to do with treatment, just may be the effect of time. Right?
What exactly does regression to the mean mean?
Regression to the mean means that if you score at time 1 an extreme score, then you're much more likely to have the next score come back closer to the mean, rather than continuing to go out to the extreme. Okay? This is a big issue in treatment studies, because when folks come in for therapy, for example, do they come in?
Extremes.
Yeah, they tend to be at their worst, right? They probably tried to deal with things on their own. They could manage that, and so they need some help with it. So they're pretty distressed, right? They're kind of out on the extreme to begin with. So they'll come in for treatment, okay? Typically, in most cases, those scores will begin to moderate, so they'll regress back toward the mean. The thing is, if they hadn't come in for treatment, the scores probably would have regressed back toward the mean over time anyway. Okay? So we know, for example, the natural course of depression, it's about 6 to 8 weeks. But if you do nothing, no treatment, nothing, it's about 6 to 8 weeks. So, somebody's pretty depressed, how long do they go before they come into treatment, you think? Like, I've become really, really depressed.